derivation of the formula used for calculation of the azimuth, for example of the sun, when the height of the sun is not equal to 0. Let's start with a sphere. The sphere is, on the sphere we will project all the celestial bodies, and in the middle of the sphere is the Earth, and say somewhere here, and this point is the middle of the Earth. Okay, then here we have the point P, which will be the pole, and on Earth this is the North Pole. Say for example our meridian would be here, and we have a latitude somewhere there. That will be the dead reckoning. On the sphere we would have this as our meridian, getting through here to the point T. Point T is actually the point when you look upwards on Earth you will get in T. Then we have the sun. In our case, the meridian of sun will be somewhere here. Say here, this is the earthly projection of the sun. The earthly projection is a line from the sun to the middle of the Earth, and where it intersects the sphere of the Earth we have the earthly projection. I have a meridian over here on the sphere. Putting this through gives us our point S. Now we have a triangle. We can go from S to T, and the interesting to see is here that this is from the middle of the Earth to T. Perpendicular to that is a line which is in fact the diameter of the horizon, the visible horizon. I can call it visible horizon or something else, but that's actually the horizon we see when we are looking outside our vessel at the sea. Okay, then we can also say that from the horizon to point S, in our case the sun, is the height of the celestial body. So this will be 90 minus the height, because point T is the point straight up, and from the point straight up to the horizon should be a 90 degrees. Then we have here from the celestial horizon to point S the declination, so we have a 90 minus the declination, and from our own meridian we have here the latitude of the dead reckoning, and so this will be 90 minus the latitude, skipping the dr. Then last but not least we have over here our local hour angle of the sun, and that completes our triangle. Taking it out, I get a triangle PST, from which I would like to know the angle T. I know the local hour angle over there. I have 90 minus the latitude, minus the altitude of the sun, and minus the declination. Remember that when we had h is null, we had, so for h is null we had a very simple formula, something like the cosine of t is something like the sinus of the declination divided by the cosine of the latitude. Well, this is not the case here, but remember that sunrise and sunset is a perfect time of taking your azimuth. Well, if it was cloudy or something else, you can take it any time of the day, but it gives you some more calculation work. Well, first thing to do now is make a step to spherical trigonometry, and we have A, B, C, no rectangular angles, so this is A, B and C, we would like to know this angle C over here. I'm not deriving the formula, but in triangle ABC you could say that the cotangents of C times the sinus of B equals the cotangents of small c, sinus of the small a minus the cosinus of the angle B, our local hour angle, and the cosinus of the small a. Well, having said that, we can apply that to our real triangle. So triangle PST, giving that the cotangents of C, which is here T, times the sinus of B, which is the local hour angle, is the cotangents of C, the small c, is 90 minus the declination, times the sinus of A, which is 90 minus the latitude, minus, so that's this minus here, the cosine of B, and B will be the local hour angle, times the cosinus of the small a, which is 90 minus the latitude. Let's make this a little bit more simple. This part here we can write as the sinus of the local hour angle. That's not nice enough. The local hour angle divided by the tangent of T. That's what the cotangents means, 1 divided by the tangent. Is, oh, that's interesting. The cotangents of 90 minus D would be probably something like the tangent of 90 minus D, and the sinus of 90 minus the latitude is nothing else than the cosinus of the latitude, minus cosinus local hour angle times the sinus of the latitude. That's this one over here. We can change this one here because the tangents 90 minus D we can write as first this local hour angle tangents T. You could also start with is, but that will be cosinus of the latitude times the tangent of D minus cosinus local hour angle sinus of the latitude. Okay, of course I could explain this step here, but you can find it out yourself. Now we're almost there. It's always a good thing. What are we looking for? We're looking for T is. Where is T? It's this angle over here, and it's the same angle over there. Okay. Then we still know what we are doing. We rephrase the thing a little bit. So we say that the tangents of T, maybe it's easier to put it this way, it's 1 times the local hour angle, sinus local hour angle divided by the whole bunch over here, cosinus latitude, tangents declination, minus cosinus local hour angle and the sinus of the latitude. Okay, that's it. Remember, this is much easier. Taking your azimuth at sunset, sunrise, go for it, because this is quite some work. Not impossible, but this is easier. Thanks for watching this video.